the point is we are actually propagating the max values to neighboring regions.
Yeah, I can see what is happening.
Yeah. Okay, so okay, so in this case, yeah, let's just apply the simple case of 2x2 max pooling with the try size as 1. So in this case, what will be the maximum value? I mean, let's just set the padding size as 0. Okay, so in this case, it will not give us the same spatial size, which is different from applying 3x3 max pooling with the padding size as 1. So we are considering a different case. But I'm trying to explain the effect of max pooling with the overlapping kind of windows, or the stride size as smaller than the filter size. So in this case, the max is 2, right? And then if we apply the max pooling over here, and then what is that? The activation map will be 8, right? And then moving it to the right, and then the activation would also be 8, right? So if we imagine it, and then 8 will be propagated in this manner, right? So the single strong kind of signal or strong activation value is propagated to the neighborhood region, right? So if that activation value was was indicating the strength of observing maybe cat's nose, and then cat's nose was found really strongly at this particular position. But when applying the max pooling with the overlapping windows or stride size smaller than the filter size, and then we are just propagating or duplicating this value or this value to neighborhood regions, so that, okay, so even though the cat's nose were found strongly at this particular position, but at in the next layer we are just giving, or we are just changing this input activation map in a way that, okay, that strength was found also in these neighboring regions. Okay, so that's the intent of applying max pooling with the overlapping windows. Does it make sense? Yeah, or what's that? Yeah, but essentially max pooling is actually intentionally losing some information, right? So for example, if we apply the max pooling over here with just the typical setting with non-overlapping windows, so for example, the activation map will be also 2 and 8, and the spatial resolution for the horizontal or width will be reduced from 4 by 2, right? But we typically think of this 8 is actually the representative of this part, right? This part. So when, I mean, from the later layers, it is viewing our image, or it is viewing our input as having 8 at all the different, I mean, at every different positions. I mean, so it will be kind of equivalent to like having 2, 2, 2, 2 and 8, 8, 8, and 8 in a full resolution. Okay, so when converting this information into the full resolution of our image, and then the later layers will view, or will consider our input is looking like this. Although it is not a rigorous kind of explanation, but max pooling is essentially the step of losing information intentionally, right? So that we don't tell, or we don't actually ignore where this 8 came from among 4 different possible positions, right? So that way, yeah, our neural net is having the flexibility of like slight deformation of some kind of shape, right? Yeah.
So does it help in making the model less prone to overfitting?
Yeah, kind of, yeah.
But am I right to say that if let's say the image that we are working with has very little pixels, then we probably shouldn't be doing this?
What's that?
If the image that we are working with have very little pixels, then we shouldn't be doing this. Should we do max pooling if the dimensions are actually very small? So maybe like in your example, it's 4 by 4 pixels, right?
So
then probably doesn't make sense to do max pooling.
right, yeah. So if our original input image is already 16 by 16, and then yeah, we cannot apply more than 4 times of a max pooling with the window size is 2 by 2, right? Because it will go into like a sub-pixel level. I mean, we need the pixel actually smaller than our original single pixel, right? So in that case, we have no other options applying more max pooling. So in general, it would be great if we give a higher resolution of an input, and then it's generally the performance or accuracy will become higher. Yeah. Yeah. But yeah, typically, yeah, if you build your own model, and then it will take the same size of an input. So you just have to fix your input image size as maybe 128 by 128 or 64 by 64 or even maybe 32 by 32. So it's your choice. I mean, it's not directly. I mean, it's not related to the data set size, because you can always resize your input images, right? So once you have a smaller size of an input image for your model, and then yeah, it will be trained much faster, but you expect a little bit less accuracy, yeah, than the model taking a larger input image size. Okay. But yeah. But if you're interested, and also, yeah, if you're interested, and then you can just look for this. So FCN. So this acronym is for not fully connected network, but it's actually fully convolutional network. Okay, so fully convolutional network. So in this case, it can actually handle a variable size of an input image size. So in this case, yeah, by applying something called the global pooling or global average pooling, yeah, we can always, yeah, this kind of network architecture can actually have an ability to take the variable sized input images. So it is it is quite often used in object detection or segmentation, and yeah, those kind of a little bit specific computer vision tasks. So yeah, you might have a chance to discuss about it, but yeah. Any other questions? Okay, so you now understand how this pooling layer is mixed together with the other conv layers while it maintains the spatial resolutions. Okay, and let me briefly mention about how come we found this particular architecture, or so it was invented by Google, and this inception module was invented in the following manner. So we basically want to define our unit that is composed of multiple different branches, and at each branch it applies different types of neural nets, like max pooling and maybe 1 by 1 comp, and then maybe 3 by 3 or 5 by 5 comp, and so on, right? So once we have this kind of flexibility to define one particular unit in our neural nets, and then there are so many different possibilities, right? And so what Google did was, or yeah, this is also called sometimes it is a called the auto ML, or kind of automatic machine learning, or it is called the architecture search. Okay, so this architecture search, the main job of it is to find the optimal, particular architecture that will work best for our own task. Okay, so here the particular task of our goal is just the ImageNet classification. Okay, and then Google actually applied all the different types of variations to define one particular module, and then they just stacked that particular module over and over. So that's how they constructed this GoogleNet. Okay, and so the key part is to find optimal architecture that will form our, one unit of our layer, right? So so there are many different optimization algorithms. So how we design this particular module is actually not trivial, and that is not done by our gradient descent, right? So our gradient descent will require a fixed neural net architectures, right? So before applying or before running our gradient descent modules, we actually have to define prior to running this gradient descent. So designing or determining the optimal architecture is actually our role, right? So it means human has to take care of that part, right? So that way, that kind of manual part or kind of human side of tasks, we want to automate them. We want to even automate that part, which is still left at the human side by doing the manual kind of search, or manual kind of repetitive, like trial and errors, right? So that way, this auto ML isn't kind of an effort, or the research areas to kind of automate the human side of the tasks when doing the machine learning, which is beyond this gradient automatic gradient descent optimization. Okay, and one example is to optimize our hyperparameter, such as a learning rate, and also another hyperparameter is just to design our particular module that will work optimally for our own task. But this optimization, this finding out the optimal design of our neural net is a lot more challenging than just finding out the optimal learning rate, because that is, that falls into the category of categorical or combinatorial optimization problem, right? So if we found the particular learning rate is too high, and then we have a notion or sense of like how to change this parameter. If it was too high, or if the objective function blows up, and then we now have the idea, at least we need to reduce this parameter to a smaller value, right? But in this architecture, if this architecture is not optimal, and then where to change, and into what kind of modules, right? So in that case, it is a really combinatorial. We have to do a lot of trial and error by mixing and matching a lot of different modules, right, with the different orders and so on, right? So there are, this is called the combinatorial optimization problem. By searching through many different combinations of possible choices, and then we want to find the optimal solution, right? So there are not many kind of combinatorial optimization techniques that works pretty well, but there are a certain method, and one of them is also one of them is called. Have you heard about this genetic algorithm? So there are several different algorithms that can be applied to the combinatorial optimization problems, and then Google did a lot of work or basically running their powerful machines to run this combinatorial optimization algorithms to find out what is the best module's definition, or this kind of particular structure. And this is one architecture found by Google at that in that era, or in 2014, right? And then Google continues to this kind of research, and also it has to run or perform really large number of this trial and error kind of thing by changing this module. What if we change it into 7 by 7, and then what if we just apply this max pooling over here? So sequentially, or in parallel, there are so many choices. So Google actually found one particular optimal kind of module through some combinatorial optimization algorithm, but there is no magic there, and so it has to run really many different architectures and then find out the best one. And so it requires a lot of computational kind of machines, or so Google or Facebook and those really large companies are just doing the research in this field, but not many from the universities or kind of individual basis. But anyways, they continue to do some search, and so they apply some interesting algorithms from reinforcement learning and maybe some other algorithms to find out the optimal architectures. And so if you are interested, and then you can also do your own project in that direction. Okay. Any questions? So let me. So I believe I covered this inception module. So if you still have a question, please let me know. And this is a batch normalization. I mean, the main goal of this batch normalization is to provide the proper range to the nonlinear units, so that the gradient doesn't get killed, right? Or the input activation or output activation values are not saturated or remain just as 0. And so it is mainly used just before the nonlinear activation units. So once, if we use it just before convolution layer, and then even if we change, or basically batch normalization is scaling and shifting our activation values, right? And shifting means we add some bias or some value, and the scaling is just multiplying particular value to our input activation value, right? And so in that case, the convolution is just nothing but a linear combination, right, of the input. So our convolution parameters plays a role of scaling and shifting in their own manner given the input activation maps, right? So batch normalization doesn't need much before the conv layer. So did it answer this question? If you guys have more questions about it, let me know. Okay. Okay, and also let me briefly explain these modules. Okay, so basically you understood the basic intent or the role of this module, right? So even though our GoogleNet is composed of many inception modules, or maybe 10s or 20s and so on, but after maybe 4 to 5 inception module layers, and then we just directly pass it through their own fully connected layers. Okay, and then we get the output in terms of our 1,000-dimensional softmax vector to just compute their loss with respect to the ground truth probability. Okay, so in this case, even though this whole network is our main goal that we eventually want to obtain, but yeah, stacking these layers more and more, will make our training more difficult, right? So in the ancient age or in the older ages, if you watch it, this RNN's like lecture videos, and then you probably remembered that Justin, when Justin recapped this part, then Justin mentioned that this kind of network training scheme is used before the invention of this batch normalization, right? So if we didn't have a batch normalization, and then when stacking these layers, and then it will easily make our network not being trained at all, right? Due to this gradient vanishing or improper ranges given to the nonlinear activation units at some point, right? So it will make our training process really difficult, right? So in the previous errors, we actually used this kind of strategy. So even though, even if we want to obtain, we want to train or maybe 20 layers, we just, first train only 4 or 5 layers first. And so it doesn't exist at all at first, and then we only train this part by using or by applying the loss at this particular layer. Okay, and then now this part will get trained to produce kind of suitable to extract some suitable patterns, right? And then now we kind of make or we make this lower layers stable at first, right? And then we stack more layers, and then apply this part, okay? And then this part will get also trained, and also this part will get also like fine-tuned, right? So fine-tuning means, so this part was once trained by using this shallower version of our network, and then we throw this part away, and then instead we stack more layers that we want to add, and then we have this part, right? And then we now apply this loss function at this point, and then this part is starting with the random initialization, right? And this part will start with the previously trained parameters that were once optimal for this shallow version of our network, right? And then we either not train this part at all, or we apply the learning rate as really small value, as maybe 0.01, and then for this part, because it starts with the random initialization, it has a long way to go to converge as their optimal values. So in this case, the learning rate could be 0.01, which is much larger than this value. So that's that was kind of how we kind of stack, or how we train this deep neural net architectures, like one by one, or kind of lower layers first, and then stack more layers, and then train that part, and then once they become stable, and then we stack more layers. So that's how we train this model. Okay, but nowadays we don't use that strategy at all, right? Because we have a really powerful tool of a batch normalization. But when they are working on this Google net, it is how the entire neural net is trained. Any questions? And also, alternatively, we can actually utilize, we can actually train this model simultaneously. I mean that. Okay, so we have 3 outputs, right? And then it will give a 1000 dimensional softmax vector, and also we have 2 different versions of 1000 dimensional vectors, and then we apply the same one-hot vector, which is our ground truth, at this position and this position and this position, right? And then we can actually train this network by using this 3 different points of our neural net outputs all simultaneously. So in that case, yeah, so this one is giving us like cross entropy loss, and this one is also giving their own cross entropy loss, right? And then our objective function should be scalar. So if we consider different losses at different positions, and then they should be added together at some point. So our loss function should be something like this, okay, which is a linear combinations of the different losses that we consider. So that way we just produce one single scalar output, right? So in this case, this alpha, beta, and gamma is our hyperparameters. So in this case, we can maybe design this alpha, beta, gamma, and their sum as 1. Okay, so without kind of losing any kind of generalization. So it is just the equivalent. I mean, because it like applying this and then maybe applying this will produce the same output, because it's just a matter of scalar multiples in terms of our loss function value. Yeah, it doesn't affect the optimal parameter value, right? It doesn't change that. Okay, so in this case, if we just apply like 0.98 and 0.1 or 0.01 and 0.01, and then it is giving much higher weights to this part, right? And then if we have maybe 2 and 3 and 5, and then we are giving more weights on the last part, right? Okay, so if we're gonna train this model by using these 3 different loss values simultaneously, and then you can actually change these parameters during the training time. Okay, so that way, in the first stages of a gradient descent, and then you apply this kind of weights, because it will be difficult to train using the third loss, which is the output after stacking a lot of layers. I mean, that will be really difficult anyways in the first stages of the gradient descent, right? And then you just gradually decrease these values and increase these values, and then during the single set of the gradient descent iterations, you can actually change these hyperparameters in a way that these values become larger and larger, and this becomes smaller and smaller, right? So that is also another kind of strategy by using all the losses, produced at different positions. But whether you just exclude it, we just ignore this part, and then you just train this part first, and then once they are stable, and then you just stack the second part. I mean, that is the first strategy that I explained, right? So in this simultaneous version and the sequential kind of stacking version, there are 2 different strategies available. But both of these cases, once you finish your training, okay, once you finish the training, and then this whole part is gone. Okay, we don't actually use them at all at the test time, because we actually want to use the output, at the really deep neural net that we intended. I mean, with the large number of depths that we originally intended. Any questions? So, yeah, in this case, we now involve our loss function. I mean, our loss function is involving multiple different terms, right? So even though they are all the same kind of cross entropy term by applying the same ground truth labels, but they are actually using a different outputs, right, at the different layers, right? So technically these three terms, 1, 2, and 3 are different loss terms, and then we linearly combine them, and then in general it is called the multitask learning. Okay, so this is called the multitask learning. So why is it called the multitask learning? Yeah. So in this case, let's look at this lower layers or lower level of our network. So that lower layers should be utilized in order to minimize this part, and also in order to, it should be minimized. It should minimize this part and also this part, right? So at this position, I mean, the output at that level, should satisfy multiple different criteria or objective functions, right? So that way, the task that this layer output should achieve or should take care of is actually composed of different tasks, right? So that's how we call it as a multitask learning. Okay. So this kind of multitask learning, I mean, one simplistic example will be like regularized version. Okay. So if we imagine linear regression or logistic regression with the L2 or L1 regularization, and then we can actually draw our computational graphs like, let me add one more explanation about this. So in this case, our loss function should arrive at the single node, right? Because our loss function is always scalar value, right? So in this case, if we just finish or complete our computational graph by using, for example, this kind of a hyperparameters, and then it will be like this times maybe 0.2, and this times, I mean, we will have the node that will compute the cross entropy loss, and then it is multiplied by, it gets a little messy, but and then it will be multiplied by 0.5, right? And then they are added together. So this is our full computational graph, right? And then the loss is computed at this point, and then it will be backpropagated through this multiple branches, right? And so if you imagine this regularized version of linear regression or logistic regression using L1 or L2 regularization, and then we will have our data. I mean, this is really conceptual figure, but this is our parameters, right? And then we have our data fitting loss, which could be cross entropy or L2, I mean the least, I mean squared loss in terms of linear regression, okay? And also these parameters are also branched out into L2 regularization paths, okay? And then using some regularization parameter that is assigned to this regularization term, and then we will have this final node in our computational graph, right? So in this case, from the perspective of our parameters, that should minimize the loss incurred by this position, and also the loss incurred by that branch or that kind of different kind of routes in our computational graphs, right? So in that sense, our parameter should satisfy two different criteria. So that way we call it, we can call it as a multitask learning. Okay. And also another multitask learning example would be, have you learned about the autoencoder? Autoencoder. Does anyone know autoencoder? Autoencoder. Okay, anyone not knowing the autoencoder? Doesn't know autoencoder at all. Okay. Okay, so yeah. So autoencoder is something like this. So suppose we have some facial images. So we collect the facial image of each person in this room. Okay, and then suppose we want to build up our classifier of determining the gender of a person, whether he or she is a male or female. Okay, and then our gradient, suppose we just built up our convolutional neural net, and then at some point it will be composed of a fully connected layer, right, which has the spatial resolution of 1 by 1, and then after then we will obtain one single scalar which will pass through the sigmoid layer. Okay, and then if it is a 1, close to 1, and then it means a woman, and if it is a 0, and then it means it is just a man, right? So that way we can build up our kind of binary classifier, right? So in this case, we can actually design this multitask learning by incorporating something called the autoencoder, and autoencoder works as follows. So suppose at some point during our convolution layer, it is having maybe suppose it is 4 by 4 by 3, right? 3 is RGB channels, and then the spatial resolution is at some point reduced by 2 by 2 and 128, for example. And then now using this activation, we will just pass it through the rest of our neural nets so that it produces one single scalar output indicating male or female, but also this output is actually going through the another branches of our neural nets. Okay, and then by just carefully setting up our parameters in our convolutional neural nets, we can actually increase the spatial resolutions as 4 by 4, and then also suppose at the last convolution layer. So in this part, it's a really sketchy figure. So suppose at this point, so this is a conv layer that has the filter size as the number of filter as 3. So in this case, we have a 4 by 4 by 3, okay, and then we of course have the input images that will fill out particular values in each of these elements in our tensor or 4 by 4 by 3 activation map, which is our input image. And then this guy, we intentionally obtained the same size of an output activation map as the input activation map. And then we just apply the L1 or L2 loss element wise in this manner. Okay. So in that case, so this pixel, so this RGB, and suppose this was 111, for example. Suppose the pixel values at that position was 111, and then after going through some conv, and then at this point it is branching out into 2, and the lower branches is transformed into 4 by 4 by 3, which is the same size of an activation map as the input. And then Suppose this value was maybe 83. So in this case, we can actually generate the loss as the difference between these two, which is 111 minus 83. Okay, and then in this input activation map, we have 4 by 4 by 3. 48 different pixels, right, in our input activation map, and also we also have the same number of output elements in output activation map, right? And then we just compare this element-wise, these values element-wise, and then we just sum them up, and then we can think of this L1 loss generated by each pixel in our output activation map, right? So in this case, we have the L1 loss, as the summation of all the loss generated by the element-wise manner by just comparing input and output activation map. So let's call that term as the second term, and then so here we have our original task and its loss function, which is defined as binary cross entropy, right? So if that person was like female, okay, and then it is it has the label as 1, okay. So if it is a person, this person is a male, and then it will have the label as 0, and that way we can just consider the binary cross entropy in this manner, right? So in this case, we can apply the same kind of strategy of satisfying both of these criteria, like 1 and 2, and then we can consider their hyperparameters, which is like weight values assigned to each of these loss terms, right? So if we imagine this L2 or L1 regularization, and then our task is fixed, right? So so in this upper figure, so even though our training objective function involves or includes that L2 regularization term or maybe L1 regularization term, our main goal is to maximize the performance of that data fitting on the test data or unseen data, right? So in that case, this L2 regularization term is actually kind of an obstacle that actually prevents us from maximally fitting our training data, right? So that way, the bottom part or that L2 regularization works as regularization, right? So the main idea is not to maximally fit our training data, right? How do we do so? We actually have an additional loss term in our loss function, and that way we have to minimize the lower part as well as the upper part. So that way we kind of avoid maximally fitting the training data only, right? So eventually or empirically, it gives the better accuracy on the unseen data, right? So that is the main idea of the regularization, right? So the lower part is working exactly in the same manner. So here our main purpose is still distinguishing or classifying male or female given a person's image, right? So this lower part of our objective function or objective term is not our it's not our goal, right? So by combining these upper part and the lower part of 1 and 2 in this manner, okay. So this is our objective function. So we are not we are not optimized the first term, but we have to care about this second term to minimize that as well, right? But eventually, once we apply the model trained that minimizes both of these terms in that combined form, okay, so that will work better for the unseen data, right? So that way it works as a kind of regularization kind of effect. And the main kind of plausible reason or reasonable explanation about why this kind of thing works as a kind of regularizer that improves the test data performances is because so once we suppose our training data had all the female person's images as having kind of longer hairs. Okay, so again, our training data has all the female images as those having the longer hairs. And then if you remember kind of dropouts and those kind of regularization stuffs, and then our model will be easily prone to getting overfitted by just focusing on the hair part, right? So again, our training data has the like female images all having the long hairs, and then our model will be trained by just focusing or by only looking at this long hairs, right? But what if our test data has the woman's images that has short hairs? So in that case, our model trained by using this limited training data will not perform or will not generalize well for those unseen data because that has these unseen patterns, right? But in this case of so this lower part is called the autoencoder because it actually encodes some images into some activation map, but it has to be converted into, it has to be converted back into these original image, right? So that way it is called the autoencoder because this auto means it's not like automatic, but it's it has the meaning of the self, right? So it's like self encoder, right? So if you know the term of orthography, what is the meaning of an orthography in Korean? orthography means 자서전이죠. 자서전 그러니까 남이 내 뭔가 인생을 써주는 게 아니라 내가 내 인생을 쓰는 게 자서전이잖아요. 거기서 이제 오로가 자기가 썼다 해갖고 그게 오로거든요. 네, 그래서 이 오토 인코더는 뭔가 자동으로 인코딩을 해주는 게 아니라 자기 자신을 인코드하는 거라. 그래서 오토 인코더예요. Okay, so the lower part is called the autoencoder. So if we add this autoencoder part as our part of our multitask learning framework for our kind of own task, whether it is a gender classifier or maybe age classifier or facial expression classifier, okay, so we have our own kind of goal or task, but this kind of autoencoder works as kind of is added as a regularizer to our module, and then this part, okay, this encoder part should actually satisfy this gender classification task and also this autoencoding task, right? And so if you imagine this autoencoder part, how can we perform well on this autoencoder task, right? So if our network, if our task is just to discriminate or classify the genders, and then it will be kind of easy because we can just focus on a specific kind of part out of the entire image. So it will not properly learn about the various kind of characteristics of our face, right? So our face has a lot of different kind of semantic meanings. Whether a person has a small eyes or large eyes, or maybe and skin tones and so on, right? So all the different components existing in our to represent our facial images, among them our task may require only a specific part, right? So but on the other hand, in the case of this autoencoder part, in order to reconstruct for each image we want to reconstruct it into the original kind of images, and then we should be able to learn, or we should be able to remember all the different characteristics of our images. So that way, this part is not even enough to just focus on or just to remember or encode like a hair part. Okay, so in order to reconstruct the original images, it has to remember or encode all the various semantic informations available in our facial images. So that way, it can encode some semantics of skin tones or maybe shape of an eyes and so on. So all the different information is encoded in this part, and thus it will help to perform our main tasks much better for unseen data as well. For example, even for those unseen patterns of female images having short hairs and so on. So does it make sense? Any questions? So this autoencoder, I mean, we will study this autoencoder, and it's a more advanced version called the variational autoencoder in a later lectures. So and also this autoencoder is quite widely used. So it's quite important part. Any questions so far? Okay, so we touched or discussed about really important concept of multitask learning, right? And also this autoencoder part. So it's a quite important part to remember. And let me discuss briefly, hopefully, about this ResNet. So one question was about the main intuition of this ResNet. Okay. So in this case, the main point of this figure is that we stacked more layers from 20 to 56, and then for this test data, even if we used a much complex model that has more layers, and then it may happen, it may quite happen for the test data, it works worse than the lower layer model, right? So it's a more complex one, and it's a simpler one, and sometimes complex ones works worse than the simpler ones for the test data, right? And that is because overfitting. That is because of the overfitting, right? But in this case of a training error or training data performances, it actually doesn't make sense at all, because if we used more complex models, and then in general we have more number of parameters involved in our model, and then we have so we should have a better performance by using a more complex model than the case using a simpler model, right? So at least in the case of training errors, this complex model should be below this simpler model's performances, right? But people actually tried this complex model by stacking more and more layers, but they found this weird or strange phenomena. Okay, so people thought about why it should happen that way, right? And so in general, it can be viewed. It could be due to the limitation of our imperfect gradient descent algorithm. So gradient descent algorithm, when using it to train a more complex neural net architectures, and then it might be prone to like worse local minima compared to this simpler models, right? So that might be one kind of explanation. But anyways, in practice, when using this complex model, and then it works. I mean, it works worse. I mean, than the simple model, even for training data. So it didn't make sense at all. So yeah, so in order to overcome this issue, people actually I mean, this guy Kai-Ming He invented this residual network, and then his hypothesis is as follows. So suppose we have maybe 20 layer neural net, okay, and then suppose we added one more layers, okay, and then if this 21 layer performs just as good as this 20 layer model, and then this part should work just as an identity mapping, right? So in that case, this 21 layer model will work exactly the same as 20 layer model, right? But that is actually difficult to obtain, okay? So that is his hypothesis. And how can we achieve the identity mapping in this layer? So again, the situation is that, okay, 20 layer is just enough number of layer for our own task. And then if we use more layers added at the end, and then if that added layer works as an identity mapping, and then it should just work as the same as the 20 layer model. So in that case, how can we achieve this identity mapping? So for example, suppose this additional layer is having 3 input node and 3 output node. And then what will be our identity mapping? Yep, our identity mapping will be like, so this guy is 1 for this direction, and also this guy is 1, and this guy is 1, and also this and this should be set as 0, right? So among many parameters, some selective ones should be set as 1 or trained as a value of 1, and then some other, I mean the rest of them after except for these selective ones should be learned as 0, right? So that's how we achieve this identity mapping, right? Or in this case, if we have an input vector and output vector in this form, and then y is also y and x are both three-dimensional vectors, and then our input vector x, and then this identity matrix should have this form, right? So 3 of them should be 1, and the rest of them should be 0. And so, I mean, among many different parameters that we need to optimize or train during our gradient descent, and then achieving this simple, I mean, although conceptually it is simple, it is sometimes difficult to find that this kind of values as our final or optimal kind of local minima or optimal points through our gradient descent iteration, right? Okay, so that way, he just or Kai-Ming actually changed this structure in a way that you guys know the rest of the stories. So we are adding it to the output, right? And then in this case, if we just need the identity mapping on the additional layer that we actually we added at the end, and then this matrix should just be enough to just produce, I mean, it would be just okay to just learn those parameters all as the zeros, right? So in this case, if we add the original vectors, and then by just simply learning or finding out all the optimal parameters as zeros, and then there's no no issues of selectively optimize some parameters as 1 and then the other as zeros. Okay. So yeah, training kind of this kind of pattern is much easier. And so that is the main idea of this ResNet stuff. Okay. And then also in terms of this gradient flow, I mean through the backpropagation, the dy arrived at this point, and then it actually had, yeah, this guy is these two branches, right? So two branches, and thus gradient will also flow through this direction and this direction. And then in this case, yeah, if this part was not trained properly, and then yeah, this part will be multiplied with the dy to produce the gradient with respect to this dx, right? So in that case, if this part was not properly trained, and then the gradient through this layer will also be yeah, a little bit kind of garbage kind of information. So yeah, so this is not trained at all, and then gradient will not be reliable. Okay, so in that case, this gradient is just backpropagated with an untouched state, or without any kind of distortion. It's just a backpropagated to this input variable. Okay. So that is also another kind of advantage of this ResNet. Yeah, and let me add one last remark on this ResNet. So in this ResNet, input and output activation map, if it is a fully connected layers, and then I just gave the example of having a fully connected layer having with the same input and output activation maps, I mean size in terms of a size. So what if we have different activation size between input and output? In this case, can we apply this ResNet or this skip connection? So it is not, because we have a 3-dimensional vector, and then in terms of an output, it has 2-dimensional vector, so we cannot add them together. So in the case of, when applying the ResNet, it is impossible. So input and output should have the exact same size of an activation map. So in the case of convolutional nets, for this conv layer, so it should maintain the same spatial resolutions as well as the same number of channels between input and output. That way, that's how we can add those two tensors into one tensor. Okay, so that's one limitation, or that's one kind of important characteristic. But in the case of a dense net that we studied in the later slides, and then it is just works as a kind of concatenation between these two input and output activation maps. So in this case, the activation map size can be different. Okay, so the time's already up. So that's it for today. And so then this Wednesday, so you don't need to watch any more videos. Okay, then we will continue this RNN and the attention models in the next lecture. Thank you.
저번 시간에 하셨던 것 같은데
네.
이거 어디서 1로 맞춰주는데 정확히 어떤 의미인지 알고가 다르네요.
아, 네. 이게 이제 오브젝티브 펑션에서 이게 그러니까 우리가 x제곱 플러스 2x 플러스 3의 이거를 미니마이즈 하겠다라는 거에서 여기 이제 아르그민 x에 대해서 아르그민을 하겠다라고 하면 이때는 이게 아르그민은 x가 이제 마이너스 1일 때잖아요.
네.
이건 당연하죠. 근데 이제 여기다가 중요한 건 2배를 해줘도 이 솔루션은 바뀌지 않죠. 마찬가지로 아까 그 뭐 1번, 2번, 3번 로스가 있을 때 여기다 예를 들면 1, 2, 3을 해갖고 더하는 거나 2, 4, 6을 해서 더하는 거나 이거 똑같아요. 네. 그렇게 되면 결국은 이거를 전체적으로, 그러니까 상대적인 그 레이시오만 중요하지 이거 값 자체를 전체적으로 올리느냐 낮추느냐는 의미가 없어요. 그러니까 그게 이제 일반성을 잃지 않고, 네, 일반성을 잃지 않고, 그래서 알파, 베타, 감마가 이제 1이다라는 요 내에서 알파, 베타, 감마를 우리가 고르면 되는 거죠.
아, 네.
그 얘기를 한 거예요.
아 그냥 비율로 바라볼 수 있다 약간 그런
그렇죠.
의미에서 아 네.
비율만 상대적인 비율만이 중요하지. 네, 전체적으로 같은 비율을 유지한 채 그냥 전체적으로 2배, 3배, 4배 혹은 뭐 네, 이렇게 되는 거는 그 옵티멀 솔루션 값 자체에는 영향을 주지 않는다.
아 그러니까 저는 혹시 그 1로 만들어서 비율을 만들어야만 어떤 식으로 이용할 때 쓸 수 있다거나
네,
그런
그건 아니고 편의상.
아 네.
Alright, so the way you explained the autoencoder, the way it sort of
Mhm.
takes some a set of data and basically represents it as a vector, right?
Right.
That sounds an awful lot like word to vec. Are they different or the same sort of thing?
They are almost the same.
Okay.
So in the case of a word to vec, so we give an input word,
Yeah.
and then the output word is not the same as an input word,
No.
right? So it is a context word or something
Yeah, but it
like
constructs
that, right?
embeddings, right?
Yeah, yeah,
Can
but-
you sort of put those embeddings in some sort of the same meaning
Right,
as,
yeah,
as
it's
the
almost the
layer
same.
of an autoencoder?
So yeah, in the case of a word to vec, the only difference is that the commonality with the autoencoder is that input and outputs are both words, which means that they are those input and output vectors are living in the same space. Right? So in that case, only the at the same input and output space, which is a kind of a word like a one-hop vector kind of a space, and then input and output are not exactly the same. So we have a particular pair of an input and output words. But in terms of the architecture, it is almost the same. It is encoded as some vectors or some activations, and then it is decoded into word level vectors.
Yeah, so the output of the autoencoder would be just some abstract sort of set of values that are sort of reduced into a lower
yeah.
space, basically.
So in the case of a word to vec, we are using this part
Uh-huh.
as a final output, right? So in the case of that's I think it's the same. So in the case of autoencoder, so we basically utilize this encoded representation for some other tasks, or, such as this guy.
Okay. Okay. That's good. Thanks.
구글에서
네.
인셉션 그거 있잖아요. 그쪽에서
네.
원바이원만 해주는 그 부분이 있잖아요.
네.
원바이원 컨버레이션 굳이 그거를 해줘야 되나요?
네. 그러니까 그거를 해주는 이유가 이제 컴퓨테이션 세이빙 때문에 그래요. 그러니까 여기서 아까 그 얘기를 마지막에 좀 명시적으로 안 하고 끝을 맺은 감이 있는데 이제 여기서 이거에서 이제 3바 이상 컴보를 걸면 이 하나의 3바 이상 컴보가 이만큼 액티베이션 뎁스를 256을 가져야 되잖아요. 근데 이렇게 원바이원으로 한번 줄이면 3바 이상 컴보를 걸면 채널이
요거는 그 채널 줄이고서 이렇게 함으로써 그
파라미터 수를 줄이는 거죠.
그 이해가 되는데 이쪽 부분은 굳이
이쪽이요?
네, 해주는
이쪽이요? 이쪽을 그래요. 그것도 좋은 질문이고요. 이쪽을 해주는 이유는 이제 이 256개의 디멘전으로 이루어진 그러니까 256개의 숫자들을 각 위치에 있는 이 256개의 숫자들을요. 우리가 어떤 형태로 리니어 컴비네이션을 해주는 거잖아요. 근데 그거를 128개의 서로 다른 방법의 리니어 컴비네이션을 해주는 거죠. 그쵸? 그게 원바이원 컴보의 의미죠. 그죠? 그러면 그것들이 어찌됐건 난리니어 유닛을 이 뒤쪽에서 우리가 걸어주니까 렐로를 통해서 결국은 그러면 여기 256개의 그 정보들이 산재에 있었는데 그걸 어떤 형태로 우리가 그러니까 스페이셜 레졸루션 보진 않지만 이 256개의 이 정보들을 그러니까 한 위치에서 발견된 이 256개의 정보의 조합들을 이런 리니어 컴비네이션 코에피션트를 적용해서 우리가 뽑고 싶은 어떤 새로운 조합으로 만들어서 거기다가 또 난리니어러티인 렐루 같은 거를 적용을 해주니까
약간 좀 새로운 필터를 만들어내는.
네, 맞아요. 이 256개의 정보를 새롭게 이제 막 뒤섞는 어떤 128개의 방법을 정의를 해주겠다는 거예요.
이번에 들어오는 텍스트 월드에 대해서 1로 지정해주고 그러니까 이게 원합 벡터로 만들고 그 다음 포스트가 마이너스
그 구글에서 알파, 베타, 감마 이걸 각각을 가진다고 하셨었는데 혹시 그러면 맨 처음에 테스트 해볼 때 알파, 베타, 감마 각각에 대한 거는 자기가 직접 해야 되잖아요.
이거 하이퍼 파라미터가 직접 해야 돼요.
초기에 각각에 대한 비중을 어느 정도씩 해야 된다 맞건
이게
정석적인
네, 그러니까 이게 지금 결론적으로는 이런 식으로 이렇게 아까 뭐 잠깐 얘기했죠. 이게 레이어를 이렇게 쌓는 식으로는 요즘은 학습 안 해요. 그렇게 그냥 다 쌓아놓고 이런 어그질리어리 클래스파이어라고 하는데 이런 거 필요 없이 그냥 이 전체 네트워크를 여기에 각각 배치놈만 껴서 학습을 해버려요. 그냥 전체를 다. 그러면 그냥 돼요, 학습이. 옛날에는 그런 배치놈이나 이런 게 없었으니까 이게 애초에 학습이 잘 안 됐기 때문에
일단 그 오토 인코더
네.
말씀해 주셨었는데
네.
이게 컨버션을 통해 가지고 이렇게 줄였다가 다시 자기 원래 형태로
네.
똑같이 이렇게 해가지고 이걸로 에러가 이렇게
네.
해서 학습을 한다고 하셨는데
내가 지금 너와의 차이가 없는 건 아닌데.
결국 자기랑 똑같은 걸 만든다는 거잖아요.
네.
그거를
그게 뭐 하는 거냐?
네. 죄송해요.
네, 아니 그게 또 중요한 포인트고 그거를 미처 설명을 못했는데 지금 이제 보면 어찌됐건 여기 있는 정보, 인풋에 있는 정보보다 얘보다는 우리가 보통 정보를 이렇게 차원 축소라든가 그러니까 이 더 뭔가 정보를 압축을 해요 우리가.
네.
압축을 했다가 이걸 다시 원래대로 좀 복원을 해야 되는 거잖아요.
네.
그러면 이거를 지금 사진 한 장에 대해서만 다 할 게 아니라 우리가 갖고 있는 트레이닝 데이터 100장이라 그러면 100장에 대해서 이걸 다 해야 되거든요. 그러면 100장에 대해서 우리가 다 그거를 잘 복원을 하도록 하려면 결국 이 압축할 때 뭘 좀 중심으로 찾아야 하면 사람의 얼굴이 갖고 있는 그러니까 예를 들면 여기는 그냥 사람 얼굴은 다 동그랗게 생겼고 뭐 눈, 코, 입이 대충 어디 있는지는 알잖아요.
네.
그러니까 그런 거는 얘가 그런 거는 얘가 그냥 자체적으로 그냥 그릴 수가 있고 여기서 이제 정보가 달라짐에 따라서 정보가 달라짐에 따라서 우리가 기억해야 되는 정보는 이 사람의 눈이 조금 더 찢어져 있구나 아니면 눈이 다른 사람보다 좀 더 크구나 뭐 이런 거 뭐 코는 뭐 좀 뭐 약간 들창코구나 뭐 이런 거를 기억을 해야 되는 거잖아요.
네.
그러면 그런 이제 유의미하게 우리가 기억해야 되는 정보라는 건 뭐냐면 사람의 얼굴에서 나타나는 이제 여러 가지 이제 그런 베리에이션들이라는 거죠.
그 사람만 갖고 있는 특징이나 그런 것들
그런 거예요. 네. 그래서 그런 것들을 그러니까 아까도 얘기했던 것처럼 그러니까 결국은 이제 이거를 다 원래대로 픽셀와이즈로 복원을 하려면 아까 얘기했던 것처럼 이게 뭐 성별을 클래시파이하기 위해서 이제 머리만 얘가 보고 있었는데 머리 이외에 다른 부분들도 다 복원을 해야 되니까 여기서의 정보는 그러니까 그 사람의 그냥 지금 현재 트레이닝 데이터에서는 남자 여자만 이제 보면 되는 거였는데 그거 대신 이제 다른 여러 가지 정보들을 다 기억을 해둬야 이쪽을 잘 복원을 할 수가 있잖아요. 그래서 여기서 좀 더 여러 가지 의미 있는 정보들이 이제 취약이 되고, 그러니까 여기서 그냥 머리 쪽만 그냥 정보만 뽑아내는 머리 길이만 뽑아내는 식으로 동작해서는 안 된다는 거죠. 그래서 여기서 뭔가 좀 더 리치한 정보를 이제 뽑아주게 되고 그걸 가지고 이 뒤쪽에서 뭔가 하면 더 이제 성능이 좋아진다. 약간 이런 개념이거든요.
약간 이게 개념적인 걸로 이렇게 들었을 때는 그래도 알아들을 것 같은데.
네. 그러니까 이게 한마디로 좀 얘기하면 멀티태스크 러닝이라는 게 하여튼 레귤러라이저로 아까 얘기했던 것처럼 레귤러라이저로 쓰이는 데 역할을 많이 하고 좀 이런 게 있어요. 우리가 이거를 남자 여자로 클래시파이 하는 것과 이거를 또 같은 사진을 나이로 클래시파이 하는 게 있어요. 그러면 그거는 같은 이미지가 같이 이렇게 인코딩이 됐다가 어느 순간부터는 이렇게 분화가 돼서 하나는 나이를 클래시파이 하는 거 하나는 성별을 클래시파이 하는 네트워크로 두 개로 쪼개져요. 그러면 어떻게 보면 이 공통의 레이어는 결국 이 두 개의 태스크를 다 만족을 해야 되는 거잖아요. 근데 그렇게 되면 어떻게 보면 그냥 하나하나씩 따로따로 우리가 학습을 해요. 예를 들면. 그러니까 네트워크를 아예 별도로 둬갖고
초반부터 이거는 초반은 같이 갔다가 분화가 되는 게 아니라 초반부터 그냥 완전히 다른 두 개 완전히 별도의 네트워크를 학습을 하는 거예요. 그러니까 과연 그 세팅과 이렇게 같이 갔다가 분화를 하는 세팅, 그 같이 갔다 분화를 한다는 거 같이 가는 이 초반 레이어는 이 두 가지를 다 만족을 해야 되는 약간은 이 두 마리 토끼를 다 잡는 형태로 쓰여야 되잖아요.
네.
근데 이제 트레이닝 데이터에서는 당연히 이렇게 설계를 하면 멀티태스크 러닝 이렇게 쉐어드된 파트가 있는 식으로 설계를 하면 트레이닝 데이터에 대한 성능은 각각에 대한 성능은 이렇게 따로따로 네트워크를 별도로 뒀을 때보다는 성능이 더 안 나와요. 네, 왜냐면 이거는 두 개를 다 동시에 만족해야 되니까 두 마리 토끼를 다 잡아야 되니까요. 근데 실제로 테스트 데이터에 대해서 성별 혹은 나이를 클래시파이 하는 식으로 뭔가 테스트 데이터에 대해 성능을 재보면 이거를 두 개를 이렇게 다 해서 여기가 두 마리 토끼를 다 잡도록 뭔가 만든 모델이 오히려 더 뛰어나게 돼요. 그러니까 그런 식의 이제 레귤러라이제이션 효과가 있는 거고, 그러니까 그게 이제 뭐냐면 왜 그러냐면 이 로어 레이어에 있는 요 덩어리가 이 앞단에 있는 레이어가 나이만 캐치를 하려면 예를 들면 뭐 눈매라든가 눈이 얼마나 처졌는가 그런 것만 보거나 이제 남자 여자는 뭐 다른 데를 전체적으로 보지 않고 이제 머리만 짧다 길다 요것만 이제 보다 보니까 우리 데이터의 어떤 그 레이블만이 제공해주는 차이를 그것만 이제 보려고 하는 거잖아요. 근데 어떻게 보면 이게 두 개를 다 이렇게 동시에 다 해줄 수 있도록 앞에 레이어가 이제 꾸며져야 된다는 거는 여러 정보들을 뭔가 얘가 다양하게 다각도로 좀 다양한 정보들을 좀 뽑아주도록 역할을 해야 된다는 거죠. 네, 이런 측면에서 좀 네. 그래서 둘 다 했을 땐 좀 그 테스트 데이터에 대해서의 성능은 각각을 이렇게 두 마리 토끼를 다 잡도록 설계를 하면 트레이닝은 당연히 떨어지지만 이제 테스트는 둘 다 올라갈 수가 있고요. 그다음에 또 하나는 좀 이런 게 있어요. 이렇게 멀티태스크 러닝을 하게 되면 데이터셋을 우리가 여러 데이터를 한 모델에 넣어서 학습을 시킬 수가 있어요. 그러니까 무슨 소리냐면 이게 이미지가 있고 여기서 이렇게 분화가 돼서 이게 나이고 이게 성별이에요. 네, 그러면 우리 데이터가 예를 들면 이 나이라는 레이블을 갖고 있는 데이터가 한 500장 있고 성별에 해당하는 데이터는 뭐 300장 이거랑은 다른 데이터셋이에요. 네.
네.
그러면 우리는 이제 이 500장 그러니까 이거를 이 쉐어드된 모델이 아니라 단일 모델로 한다. 그러면 이거 하나 또 얘는 이것대로 그러니까 여기 모델과 여기 모델은 그냥 다른 모델이니까 별도로 학습을 하는 거잖아요. 그럼 이제 여기는 당연히 이제 500개로만 학습이 되고 여기는 당연히 300개로만 학습이 되는 게 당연하죠. 그렇죠? 근데 이제 이 모델에서는 지금 500개는 그러니까 이게 500개가 나이라 그러면 500개는 지금 여기를 학습을 해주고 그 다음에 300개는 또 여기를 이렇게 학습을 해줘요. 그렇죠? 그럼 결국은 이만큼은 총 800개의 데이터로 학습을 하는 효과가 일어나게 되거든요. 그냥 두 개를 다 해야 되니까.
네.
그러니까 이게 좀 데이터 어그멘테이션 측면이 좀 있어요.
오히려 트레이닝 셋이 이걸로 하면
많아지니까.
더
네.
늘어나고.
네. 어찌됐건 요 쉐어드된 파트는 어쨌건 그 여러 태스크 중에 하나 뭐가 됐든 다 네. 할 수가 있었어. 그래서 이제 이런 식으로 데이터 어그멘테이션 측면 때문에 더 좀 잘 하게 되고요.
감사합니다.
네. 이해 가요? 뭐?
네.
그래요. 네, 알았어요. 네.